right. It's a great honor to be here. I'm Feihu Xu from China. So, yeah, it's the first time to be in Chile. When I got down the airport, I say, many cars, many clothes are made in China. It seems like come back to home. So, okay, so I have talked about quantum information science. The previous speakers talked a lot on the physics and also the fundamentals. I want to really share with you why we do quantum information science and what we can do for human beings. Okay, so quantum information received a lot of attention during the past few years, like the Breakthrough Prize, specifically given to the fundamental work in the field of quantum information. And also the Nobel Prize in 2022, also given to experiments with entangled photons, examining the violation of bioequality and pioneering quantum information science. And also the first speaker, Serge, also David Weiland, are the pioneers for the quantum physics and quantum information. Besides the fundamental science, most of the countries, like UK, Europe, US, and China, many countries put also the national strategy for quantum information science. So the question is, why we put so much emphasis on quantum information research? Why we like quantum technology? I first share with you two challenges for modern society. The first challenge is computational capacity. Back to 1940s, the previous speaker from IBM, the founder of IBM, Thomas Watson, said, well, in the world, we maybe only need like 5 computers. But look at now. Everyone has a cell phone. Everyone has a PC. We have the supercomputers. We have the GPU to process the large model. We have the GPT help us a lot. But with this cell phone and personal computers, the data we have today is growing exponentially every year, okay? So the world data is keep growing. But the computational power we have today is not sufficient to process such a large data. Actually, we are living in a big data society. So we can do a calculation. You can calculate, you can combine all the cell phones, all the personal computers, all the supercomputers in the world. The computational power is only about 2 to the power 90. You see, it's a small word, but if you do the mathematics, it's a very large word. Or you use all the computational power together, you can only simulate about 90 atoms within a year. So for the current digital computer we have the called Moore's law. It tells us every 18 months, the computational power will double. Or on the same size of circuit, you can integrate a double size of transistors. The size of transistor is decrease half every 18 months. So that's why back to 1970s, we only have about 14 nanometer transistor, but right now, or in the couple of 5 years, it's already below 1 nanometer. Then it comes to the quantum level. The question is whether the Moore's law still applies. Or a very general question, you can think about what the computer will look like in the future 50 years. That's a really big question. So the second question I want to emphasize is about privacy and security. We know privacy and security is always with us, with human beings. Back to the old days, we have the traditional cryptography. Back to World War II, we have the Enigma machine. And for the current society, we also need like cipher, or we can call it codes to encrypt our privacy. We call it modern cryptography. But the history tells us every advance in classical cryptography has already been defeated by advance in cracking. So actually, a big motivation called quantum computation is also the Shor's algorithm. It tells us the Shor's algorithm, together with the quantum computer, you can correct the current asymptotic, like the RSA, the asymmetric cryptography, very easily. So then come to the quantum physics. Like Serge said, this year is the year of quantum year. After 1 century's development, quantum physics already gave us some possible solutions for the previous 2 modern challenges. So the solution is we expand from the classical bits to the quantum bits. We call it qubits. Then this is called second quantum revolution. So what is qubits? So the classical bits, like the digital computer, we use the electrical voltage, high level and low level to encode 0 and 1. But in the quantum world, we have the superposition of 0 and 1. So for example, you can use the polarization of photons to increase the qubits. So it can be in a quantum state of alpha h plus beta v. So before you measure the quantum bit, it's in this superposition. So you don't know what the quantum state it is. Only after you measure it, it collapses. So this already gave us the foundation for a new kind of communication. I will talk later. We call it quantum cryptography or quantum key distribution. The other very interesting phenomenon is entanglement, which I already talked in the previous speakers. So using quantum entanglement, we can increase the power to encode information. So suppose you have 2 photons entangled, then you can create 2 qubits. This will be a superposition of 0, 0, 0, 1, 1, 0, and 1, 1. So using 2 qubits, you can process 4 classical bits simultaneously. So you can think about keep going, you have 3 qubits, then you can process 8 classical bits. Then if you have n quantum bits, you can process 2 to the power n classical bits. That's the motivation to do quantum computation. It gives us the exponential speed up to process information. So that's why we have qubits. If we can coherently manipulate this quantum system, then we have 2 novel techniques. One is quantum communication, the other is quantum computation. Also, we have quantum metrology. Previous speaker already talked. So for quantum communication, first I will share you a video.
Quantum key distribution network is an infrastructure that provides key resources for various applications. Furthermore, an open application enablement platform can be established to provide end users with quantum secure communication services. The Open Application Enablement Platform is driven by a universally adaptable engine, which is independent from operating systems, services, or application scenarios. The application can be a cloud service, a government enterprise private network, a mobile communication, an Internet of Things, an Internet of Vehicles, or artificial intelligence. Based on the application enablement platform, every developer can build user-oriented applications, shielded with quantum secure network, which services with quantum security.
Okay, so the idea of quantum communication, or we call it QKD, quantum key distribution, was proposed by Charles Bennett and Gilles Brazard back to 1984. So the idea is we can use a quantum system, such as polarized photons, to encrypt the digital information. The quantum non-cloning theorem, or the quantum uncertainty principle, gave us a very novel cryptography phenomena, which cannot be done with classical mechanics. So use this, you can generate unconditional security. You can have unconditional security to generate secure keys, and these secure keys can be used for the following up secure communications. But in the practice, a very big challenge is how you can transmit these photons, or you can transmit this quantum system over long distance. In fiber, we have the loss. So that's why if you transmit many photons, our long distance fiber, there's not too much we can survive. So we can do a calculation for a 1,000 kilometer fiber. If we have the best technique we have, or you only have to transmit 1 photon per century. That's why it's a very big challenge to do long-distance communication or build up the global quantum internet. So far, a very good solution is using the satellite, or we can do the quantum communication in outer space. The reason is if you look at the sky, the thickness of the atmosphere is only about 10 kilometers. That's why if you take plane, you basically fly above the atmosphere. Then if you have a satellite in the sky, you send photon to the satellite. The photon only need to pass this 10 kilometer atmosphere, then it will go to the vacuum or go to the outer space. That's why the photon can travel very long distance. Using satellite as a relay, we can really do the global quantum communication. So that's the idea. But it's really a technical challenge to send the photon between satellite to ground or from the ground to the satellite. There's many technical challenges, like you need to send the photon out of the atmosphere, and also the satellite moving very fast, how you can collect the photons. And also the photon is very weak. How you can do the pointing and you can detect the low energy. This is really a lot of challenge. And our group, led by Jianwei Pan at USTC, after more than 15 years effort, we launched the first quantum science satellite called MISSIS in 2016. So using satellite, we do a lot of scientific study and fundamental experiments. So the first experiment we do a quantum communication between the satellite and the ground, and then use the satellite as a relay, do another communication. Then we can do a very long distance, like between Beijing and Urumqi. So this separated by more than 1,000 kilometers. So if you compare to the transmission with fiber, we have 20 orders magnitude higher than fiber. The second experiment we do the entanglement distribution, or we take the spooky action over much longer distance. And the final experiment we do is the quantum teleportation between ground and satellite. Using the MISSIS satellite, we can keep going to do the intercontinental quantum communication, like the communication between Beijing and Vienna, and also we have many international collaborations with Italy, Germany, South Africa, and also in the future maybe with Chile. Okay, that's the basic idea of quantum communication. So the second one is quantum computation. I think previous already talked a lot. The basic idea is we can have the superposition together with the entanglement. We have exponential power to process the digital information. So how this is important? We can just play a game. The game called, we can put rice on the chessboard. It's really related to an old Indian legend. Suppose the rule is, in the first square of the chessboard, you place 1 rice. So then in the second one, we place 2 rice. Then in the third square, we place 2 to the power 2, which is 4 rice. And then you keep going, you fill all the rice on this 16-4 board, on this chessboard. Then you can calculate how many rice you can place on this chessboard. In the beginning, you think it's smaller. But if you really do the calculation, 2 to the power 16-4 is 1 trillion tons of rices. But the global rice production per year is only about 500 million, which means if you put all the rice on this chessboard, it's about 20 years of production about rices. That's how the power of exponential speed up. So using the quantum computation, we can do a lot of scientific studies, like weather forecast, financial analysis, drug designs, and also many more applications. That's also the reason quantum computation receives a lot of attention, not just from the scientific study, but also from the commercial effort. So this is a picture I got, I think, from the internet a couple years ago. A lot of big companies, all the big companies like IBM and Microsoft, put a lot of effort on quantum computing. And because of this a lot of great efforts, and the development is really fast. Here, I only just show 2 examples. In 2019, Google already did the quantum computer called SyncMore. So they do the scientific study called random circuit sampling. So they already show that using quantum computer, you can do much better than the supercomputer. And our group, just 1 year later, in 2020, we use photons, and we developed the Jiuzhang quantum computer. We can manipulate 76 photons. We also show for the mathematical problem of Gaussian boson sampling, we can also do much better than the supercomputer. So in the future, we think quantum computing has 3 milestones. The first stone is you show the quantum advantage. We already done this later. They already done already. The second milestone is we want to coherent manipulate hundreds of qubits. And really, we want to show that using quantum computer, we can do something useful, which can also outperform the current supercomputers. And the final goal is you go the general purpose, our general supercomputers. In the future, for quantum computing, we use satellite together with satellite constellation. With the fiber communication, we can build a quantum internet to provide quantum communication for the global users. And for quantum computing, in the 10 or 15 years, we want to coherent manipulate 1,000 qubits, and we can do really beat classical computer in some useful tasks. But in the far future, we can think about, actually, nature have 2 outstanding achievements for information technology. The first one is quantum laws. It gave us the lasers, the internet, the circuits, and the cell phones, the computers. The other is the human intelligence. And inspired by human intelligence, now we have the artificial intelligence, AI. And with quantum laws, we are developing the quantum computing. We think in future, we can combine the quantum computing together with artificial intelligence. So we hope we can understand and create much new intelligence, which maybe go beyond nature. Okay, that's pretty much I want to talk. Thank you so much for your attention. Thank you.